what happens in the pulse is that as the top freezes, it insulates the bottom. It actually keeps whatever heat is in there. And so whatever animal life or plant life is going to be proposed from very cold climates and makes the freeze. Whether it's underneath survives because it's being insulated. If it was freezing from the bottom up, it would continue to freeze until everything would get pushed out. And then everything would be dead.
But doesn't heat travel?
But once it hits the ice, water's an insulating medium. So it basically stays within whatever currents you have in there. Less circulated. But yes, oddly enough, the layer of water that is closer to the ice will be warmer than the one that is deeper. We just have one water section. So the closest it is to the ice, it is.
God bless you.
Bless you.
Bless you.
So we have a volume of 120 ml. A pressure of 50. Find the new volume. Here's the pressure. Just change the formula. Okay. So once again, for most of these problems, the numbers are nice, so that you can do a little bit of mental math in it. We're cutting it in half. So that means that here we're going to double. If we go through the math, we want B2, so divide by B2 on both sides. So B2 is B1. And keep in mind that once you have that, the order for multiplication is relevant. 2 times 3 is the same times 3 times 2. So that P1 times V1 times 1 over P2, that's the same as P1 over P2 times V1, or P1 times V1 over P2. Well, those are the same. As long as whatever's on top stays on top, and whatever's on the bottom stays on the bottom. My multiplication is immediate.
This is kind of what we were doing in lab, right, on Friday?
Yes.
Okay.
The first part A. So this was where you multiplied across.
Mm-hmm. I remember it.
So 120 times 2 gives us 240. Have a balloon, and the pressure is double. We're increasing the pressure from 0.7 to 1.4. So the pressure is increasing. Does the balloon shrink? Does it stay the same? Or does it get bigger? If we're increasing the pressure, it's going to shrink. So remember, that's the opposite. So we would end up with 8. So weather balloons, very simple. They're somewhat analogous to a hot air balloon, but not quite. Hot air balloon is less temperature. But in a weather balloon, basically you have a very thin fabric, So let us not add a lot to the weight, but you fill it up with helium. Up to just enough so that it begins to flow. And then once it starts rising, you need a lot of fabric to allow room to expand. You cannot inflate it completely because then it'll tear. But you inflate it with enough helium for it to begin to float. And then once it begins to float, then it will continue on its own. Because as it keeps going to higher altitudes, the pressure drops. And the higher it goes and that pressure is dropping, it begins to get bigger in size. And so as the volume keeps increasing, density is mass over volume. So since the denominator is getting bigger, the density is getting smaller. And so it becomes less and less and less dense, so it keeps going higher and higher and higher. And you don't have to do anything, just get it started, and then it does the rest of itself. A higher balloon doesn't quite work like that because it has too much weight. The weight of the basket and the individuals traveling inside. That one's for the next section, which is Charles law, temperature and volume. So, Boyle's law, pressure and volume, that's the only relationship that is inverse. Okay, where one increases and the other one decreases. The other three relationships that we'll take a look at, Charles' law, Cahussac's law, and Avogadro's law, they're direct relationships. So one increases, the other one increases also. So we see Charles' law here. If we increase the temperature of a gas sample, kinetic molecular theory says that the motion of the gas particles will also increase. So, if the kinetic energy is increasing, the speed is increasing. So technically the gas molecules are moving faster. If they're moving faster, then they're colliding more often, which means we expect an increase in pressure. So the pressure is supposed to increase. But for Charles' law, we're supposed to hold the pressure constant. So in order to compensate for that increase in collisions, we need to make the volume bigger to make the molecules travel longer distances.
So increase volume to increase distance?
Mm-hmm. And that decreases that number of collisions.
So when we were doing the lab, I had a hard time distinguishing when I would need which one. Is this the deciding factor? If it's asking to raise the volume, would that would tell us, okay, use Charles' law now? Do you understand what I'm saying? I had a hard time deciding on.
So remember, we have four things.
Or did I miss that because I was late?
Well, no, pressure, volume, temperature. So we're trying to, well, at the end of all this, we combine so that we can change more than one thing. But at first one, we want to change one thing and see how it affects something else. Okay. If you have a rigid container, then the volume is constant.
Okay, rigid.
So that means we don't have to worry about volume. If you have an open container, then the pressure is constant because it becomes the atmospheric pressure. And if you have a sealed container, then the amount is constant because gas is not allowed to go in or come out. And then the temperature, well, if you're not doing anything temperature-wise, then it's constant. If you're not heating it or cooling it, then the temperature is
In all three of those instances?
Well, this is in terms of what if we're trying to figure out what it is that you're supposed to apply it.
Yeah, and that applies to all three of those
On
instances.
experiment.
Okay, okay.
Mhm.
That's like ideal, right? Like that the temperature is constant? Or it's just kind of usually happens?
Well, no, it's on a case-by-case basis depending on
Unless the
what
question asks.
the instructions. Well,
Okay.
we're talking in terms of a laboratory setting.
Okay,
So in terms of a laboratory setting, then you look at it, what it is that you're doing. Okay. And so those are kind of little clues as to what you don't have to worry about.
okay,
Okay, so those are the things where you can, if you're not heating it or cooling it, you can ignore the temperature. Yes.
yeah,
If you don't have a flexible container, then for the most part, we can ignore the volume. If we're not sealing it, then we can ignore the pressure.
temp,
Now, on an actual problem, then you have to list what you're given, and just make a list. Pressure, volume, temperature. And we're gonna use N for the amount, which is the number of moles.
I did that, but that last question threw me out because I was just like, okay, I had all those values, but I just didn't know what to do.
Well, we're still missing something.
Okay,
We would still need to combine them. The question will change something. So that means that you will have two of something, two pressures, two volumes, two temperatures, two amounts. Then we need to keep an eye on it. And then we will ask you for something. That's the one that we're looking to see how it changes. Now it may give you one of the other values, and nothing else. That means that we assume it's constant, or it will specifically say that it is constant. So sometimes we're told exactly that it's constant, sometimes you're not told anything. Then you assume that it's constant. You don't have to worry about it. But on a paper problem, if you list what you have and see what you have two of, then that narrows it down to the law that we're looking for. So for Charles' law, then temperature and volume. So you're going to be given either two temperatures or two volumes. If you're given two temperatures, the question will ask for the volume. If you're given two volumes, then the question will ask for the temperature. Now the volume-temperature relationship is direct. That means that if one increases, the other one also increases. Okay. When the temperature is in Kelvin, then it is a linear relationship. When the temperature is in Kelvin. That means if you double the volume, then the Kelvin temperature doubles. And vice versa. If you triple the Kelvin temperature, then the volume will triple. Okay. But the temperature has to be in Kelvin for that relationship to work. If it is not in Kelvin, then all we know is that if the volume increases, the temperature will also increase, but not by one amount.
okay,
We only know by how much it increases or decreases if it is in Kelvin.
And it's by 2.
If you double the volume, then the temperature will go up too, but it depends what you do to the volume.
so it was like in that problem where we had to convert the Celsius to Kelvin, right, in the lab? Okay,
All gas calculations that involve temperature, the temperature has to be Kelvin. Every time, that means no exceptions.
so if on the test the answer is Celsius, then that's automatically wrong because we have to convert it to Kelvin?
The answer, no.
Oh,
Because, and let me just, again, real quick.
sorry.
The question may be asking at what temperature in Celsius.
Oh, that's
So you
true.
still need to do the calculations in Kelvin and then do one extra conversion at the end.
To get Celsius. Oh, that's, okay, yeah.
So you do have to be careful with
Sometimes.
that.
Okay. Sorry.
Okay, so Charles' formula, V1 over T1 equals V2 over T2. And we're either changing the temperature and looking for the volume, or changing the volume and looking for the temperature. So, we solve for V2, send T2 over to the other side, and T2 goes on top. So we have T2 on top. Let's remove it over here. T2 on top, T1 on the bottom, V1 on the top, T2 on top, T1 on the bottom. So like if you're gonna cross multiply, but you don't cross multiply, you only do one side. Because if we send this over here, then we don't have V2 by itself. The idea is to get this by itself, so just cross multiply.
Why? How do we know when to do that?
Well, here we're looking for the new volume. We're rearranging to solve for V2. We're looking for what the new volume is. If we're changing the temperature.
Oh, so only if the temperature changes, then we flip it.
Yes.
Okay.
Well, no.
Ah, crap.
It depends on what you're looking
Right.
Okay.
and what you're given.
And the thing is that when you're solving for the denominator, so if we're looking for the temperature,
If.
you do have to cross multiply both sides. So we're flipping both sides. In step one, and then there's only one step after that.
So if you're looking for the temperature, then you flip it. Okay. Hold on. V2. Sorry. I'm almost done. V1. T2. Okay, there.
Because if we're looking for T2 is on the bottom. If we want to get this by itself, anytime you have an algebraic equation and you solve for a variable, that variable always has to be on top. Because we're solving for it. We're not solving for the inverse of it. So if we're looking for T2, I need to get T2 to the top. So we have to cross multiply both sides.
Oh, okay.
And that's the first step to get T2 to the top. So T2 moves over here, T1 moves over here.
Got it.
But this is T2 still by itself, so now we need to divide by V1 on both sides. So it cancels here, and then over here, now V1's on the bottom.
That makes sense.
So when solving for the temperature, we're flipping the
And that's just depending on what you're given, right? That makes it confusing.
Yeah. That's true.
But either way, if you're looking for the new temperature, this is the formula. If you're looking for the new volume, this is your formula. So change the temperature, find the volume. Change the volume, find the temperature. So balloon has a volume of 785 milliliters of 41 degrees Celsius. If the temperature drops to 0 degrees Celsius, what is the new volume? So if we're dropping the temperature, then we expect the volume to decrease. Now by how much? Well, here we have to do the math. It's not as nice as it was
So if
before.
we do the conversion to Kelvin, then we should do that and then convert it back.
Mhm. So you line up what we know, V1 785, T1 is 21, add 273 to get it in Kelvin. The new temperature is 0 Celsius, add 273 to get it in Kelvin. So we're decreasing the temperature, we expect this to decrease. Just need to figure out by how much. So remember, V2 then is equal to V1 times T1 divided by, excuse me, V1 times T2 divided by T1. It's going to be this times this divided by this. But we'll see that before. V1 times T2 divided by T2. Okay, but the temperatures have to be cancels. So the temperature decreases, the volume decreased also. On the other one though, they were making changes that were double, halves, triple. Here though, from 294 down to 273, it's not a nice cutting it in half or cutting it in. Actually, plug in the numbers on the sample of oxygen gas, that's a volume of 420 mLs at the temperature of 18 Celsius. So we add 273 to get it to Kelvin. At what temperature in Celsius will the volume be 640? Remember, we're looking for the temperature, T2, you cross multiply, so you end up with V2 times T1 over V1. And we can put T1 in ponder and that is not. But that's what we're. So T2 is equal to 640 divided by 20. Cancel times 2.
Is it minus or times T1?
Times. Everything's multiplication or, wait, for
Oh, I'm sorry, over here.
here?
Yeah,
Yeah, everything's
it's times. Okay, sorry.
Everything's- Yeah, the only addition subtraction is to get count.
Yeah.
Okay. So 443, and you have 443 as one of the choices, but the answer is not 8. Because it's 443 Kelvin. Subtract 273 to get it into Celsius. And we get 170.
So it's just basically figuring out what formula depending what you're missing.
Yes.
Then you have to convert it to Celsius.
We're looking for V2. And then we have V1 times T2. For 8, what happens to the pressure when the volume decreases?
It decreases.
And our pressure volume, that's the one that is opposite. All the other ones are correct. The pressure volume is opposite. So if the volume decreases, the pressure
Increases.
if the temperature decreases, the volume
Decreases.
will be the same.
The same or decreases?
Well, the same that happened to the temperature.
Oh.
Not that it stays the same, but whatever. So if the temperature decreases, the volume will do the same. It will decrease.
Okay.
Not that it stays the same. This is. Okay. And then pressure volume, remember, it's opposite. So if the volume is increasing from 12 to 24, the pressure will decrease. And if the temperature is increasing from 15 to 45, then the volume will also increase. Okay. Now here, we know that if this is double, then this will decrease by half. Here, the temperature is triple, but it's not the Kelvin temperature. So all we know is that this will also increase, but not by 4 by factor of 6, just that it increases.
Man, you're flying through these today. You're flying through them today.
Well, these are, because they move, the math is similar.
Yeah.
So Gay-Lussac's law is the same as Charles' law, but instead of volume, it's the pressure. So basically, everywhere here where we see V, we just put a P. And that's Gay-Lussac's. If the volume is constant, then when you increase the temperature, then the pressure increases. If it's in Kelvin, so if you double the Kelvin temperature, then you double the pressure. And vice versa. If you double the pressure, then you double the Kelvin temperature. The volume has to be fixed. And Lussac's law is the same as Charles' law, but instead of volume, we have P. Temperature has to be in Kelvin. The pressure you can work in atmospheres, PSI, millimeters of mercury, torr, doesn't matter. But the temperature has to be in Kelvin.
Will you distinguish between which laws we'll be using on the test, or that's just something we'll have to figure out? Because how am I going to remember that I always have to do this in Kelvin?
In class, I will write notes on the board.
Okay.
And I did that lesson. On the retake, you don't need.
I know.
But on the, here in class, I will guide you.
What laws to use? Okay, that'll help.
You still need to do the algebra.
Yeah.
Like I will give you this, I won't tell you exactly which one
To use.
I will let you work to start.
But like on our cheat sheet, we could put like the laws and then, okay,
And then the variations of it.
that's great. Okay, I can do this.
So solving for P2. So P2 is P1 times P2. And solving for T2.
So, I know this is a crazy question. How are we gonna know to do this on our own though? Like when we don't have you and we're doing the HESI or whatever test you're gonna have to take to get into nursing school. How am I gonna know which law to use? Or what about when I go to testing center and retake my test because I probably failed it the first time? How am I gonna know?
The bad thing, well, the good and bad thing is that the more you practice, the easier it is to recognize. The bad thing is getting enough practice of the right type of problems before. And if you make it to the nursing program.
When? I miss
When you make it to the
Okay,
nursing.
thank you.
And I don't know where UTEP is at right now, but about 10 years ago or so, they were really good at getting you through, or teaching you so that it would be, and I don't want to say easier, but you would be better prepared to pass your boards, your own class. And it was drilled.
Okay.
Basically, every class, every semester, you were getting drilled in the type of questions that you will see in the NCLEX. In terms of dosages and calculations, in almost every class, first day of class, they would give you like a quiz on calculations. And not only could someone have, at least at UTEP, you had homework due on the first day of class.
Oh,
You
yeah.
had to check your email. As soon as you're in the program, you need to take your email to details. And on that first day of class, you're expected to already come with an assignment to turn.
That's once you're in the program.
Right. To turn in. And then they move you as a cohort.
Mm-hmm.
So whatever group you're in, you're all taking the same classes. And that helps, but they would drill you over and over and over again.
And you could
Once
use
you're in there
the
to
calculator.
do good on your boards, that doesn't quite happen with us here to get you into the program. But the more you
Which is basically the same practice, yeah.
and you have to try and visualize what it is that's happening in terms of maybe real life scenarios, but and keep in mind that one thing can lead to something else. So here, this starts out as Gay-Lussac law.
Okay.
Okay. And you have a 55, and this is actually, no, I was going to say, this is what you did in the lab.